Hello and welcome once again to Haybridge Maths Department, Year 2 Pure, where we're carrying on working our way through the Chapter 5 topic, the Chapter 5 radians, and we're going to carry on with Section 5.3, and this time we're looking at segment area. So last time we looked at a sector area. This time we're looking at a segment area. If we just draw a quick circle, let's see the difference. That's supposed to be the center of a circle. But there you go, there's a sector. Now a segment would be this area here. So you've got a chord, spelled C-H-O-R-D, that goes across from one part of the circumference to another, and the area, the side of it is called a segment. And we are going to be looking at that in this video. So let's get started with an example. If you're following along with a book, I'm doing the examples from a book, but I'm not going to solve the problems in the same way that the book does, because I think that the book introduces a formula for working out the area of a segment that's unnecessary. By all means, have a look at that formula if you prefer that. I'm not going to complain, but I think that my way, of course, is better. If I didn't, I wouldn't be doing it my way. So we're just going to do each problem using our previous knowledge of areas of sectors, areas of triangles, and combining those together. So what we're going to do on this problem is that we are going to work out, if we're going to work out the area of a segment, what we're going to do, first of all, is work out the whole area of the sector. So if we say the area of this whole sector equals a half r squared theta, then you've got a half. R is 7, so you've got 49, and we're going to times by 1.2, which is 29.4 centimeters squared. Okay, what we're going to do now is we're going to work out the area of the triangle. So the area, hopefully your notes are much neater than this is. So if you remember, the area of a triangle is a half AB sine C. It doesn't matter which angle measure you're doing, it's still that. Now what we've got here is an isosceles triangle because the top and the bottom are both 7. So what we are going to do here is we're going to do a half times 49 times sine of 1.2, and when you do that, apparently you get 22.8. And then for the last step, for the area of a segment, then what we're going to do is 29.4 minus 22.8. Now these are numbers that I've kept in my calculator so that when we do this, you'll see that you get 6.57 centimeters squared. And I think that's a better way of doing the area of a segment. There's less for you to remember, and there's so many different ways that we can ask these questions. This is better, I think, than the way the book has done it. So can you, if you haven't done so already, as I always say, pause, make notes on this, get everything down into your notes, and then we'll have a look at the next example. Okay, in this example, what we've got is we've got another segment that we need to find out the area of, but the people who've written this example have been so unkind in that they haven't given you the angle at the centre of the sector. But we can get around that. We can get around that because we know the cosine rule, and we can use the cosine rule to work out the angle at the centre. Once we've done that, it is just a case of working out the triangle, the sector, and then minusing one from the other and giving us the area of a segment. So let's get on. First of all, then we need to work out the angle at the centre. So if we call that angle there, oh my gosh, that's a terrible theta. It's me trying to do a small theta to fit the diagram. Much better. Okay, so we know our cosine rule, so we are going to say that the angle, it's the length opposite the angle, so we're going to do 5 squared is 4 squared plus 4 squared minus 2. That's a multiplied by 4 cos of theta. Then if you rearrange that, then you get that cos theta is 25 minus 32 over minus 32. So theta, when you do the inverse cosine of that, you get that theta is 1.35 little radians. Okay, so now we've worked out that angle. We've used the triangle there, used the cosine rule, something you know all the way back from GCSE. This time we're using radians, as we keep on talking about. Now let's use that angle to work out the area of the triangle. And if we do the area of the triangle, then you've got a half times 4 times 4 times sine of 1.35, and if you work that out, then you get 7.8057 ... no rounding involved there. So there's the area of a triangle. I should say, by the way, that I used a half AB sine C on that one, as we know back to our GCSE days. Half AB sine C, A and B, of course, 4, and it's the angle in between, so it's sine 1.35. Then we're going to work out the area of a segment by taking the area. Oh, I've got to work out the area of a sector first of all. So the area of a sector is going to be a half r squared theta. So it's going to be half times 4 squared times 1.35. And then we're going to do the one minus the other for the area of a segment. Area of segment, but honestly does say area of segment. Oh, I'm missing steps out left, right and centre here. The area of a sector, I should have said, was 10.8. But let's just correct myself here. We've got the area of a sector, we've got the area of a triangle. We're going to take a 1 away from the other, and apparently when you do that, you get 2.99 meters squared. So let me just run through this problem once more. To work out the angle at the centre, which we're going to need if we're going to work out the area of a segment, we use the cosine rule. Then we work out the area of a triangle now that we've got the angle, and we use a half AB sine C, and we get that. Then we work out the area of a sector, which is a half r squared theta, and we get that. When we do the 10.8 minus the 7.8057, and you get 2.99. And if you look at the question, it's in meters. So it's meters squared. Okay, so let's move on to the final example, which is, I'll be honest, a bit vicious. So let's have a look at the final example here. Now, before I even start this, I'm going to tell you something that you might not have spotted if I'm going to use it. Halfway through this example, I'm going to use a little trick, and if I don't tell you now, you're just going to go, oh, well, that's just, why has he just done that? Why has he plucked this out of thin air? It's a little sleight of hand, it's a little trick that we know, and it's something that you do need to know. We've talked about it in the past, but here it is. Here's the deal. Sine theta equals sine of pi minus theta. So whatever angle you've got, say 1, then if you take the sine of 1 and you take the sine of pi minus 1, you'll get the same answer. It's to do with a beautiful symmetry that you have with the sine curve. The sine curve has this wonderful symmetry where here's theta. Now here's pi, if you remember our angle and how it radians, how it relates to the graph. So here's theta. Now this value, when we put it into sine, will give us this value here. But if you look also across to here and back down again, this value here, that value there is the same. When you do the sine of it, you get the same value out, the same value on the y-axis. Now, what is this value over here? What is that? Now, that's going to be this, if we can work out that distance there, well, we know that distance there is theta. So what this is going to be here is pi minus theta. From all the way from here to here is going to be pi minus theta, because from here to here it's theta, and all the way across is pi. So halfway through this example, I am going to just drop in the fact that sine pi minus theta equals sine theta. It is something that we've mentioned in the past. It's something that students don't tend to, I don't know, it's not one of their favourite areas of maths perhaps, but you do need it. It's a very tricky example. This is some subtle little things going on, but hopefully with this little preliminary result, we'll be able to get you through it that much easier. Right, okay, so let me just rub out that. It will be coming back up in a minute. But what we've got here, let's have a look at the problem itself. It's saying, and it's really difficult to see, but this little shaded area here is, well, the triangle AOC is 3 times as big as that area there. So if we can work out the area of a triangle and the area of that tiny little segment, then the triangle area is 3 times as big. So how does that help us? Well, what we're going to do is we're going to work out both of those areas and then come up with this weird equation where you've got 3 theta minus 4 sine theta equal to 0. So we've got to prove this result. Now, how are we going to do it? Well, we are going to say that the area of AOC is 3 times segment area. Okay, so the area of AOC is 3 times the segment area. And what we're going to do is work out both of those. So let's work out the area of AOC first of all. Now, AOC is a triangle, and the area of a triangle is going to be half AB sine C. But A and B are going to be R because they're the radii of the semicircle there. So what we've got is a half R squared, and the angle there is going to be, it's not going to be theta because all the way round is half a circle. So if there's 2 pi radians in a whole circle, there's pi radians in a semicircle. So we've got half R squared sine pi minus theta. Now we spoke about that sine pi minus theta. We're going to be using our result in a minute, but in the meantime, let's work out the area of the segment. And in the area of a segment, we're going to work out the area of a sector, which is a half R squared theta. And we're going to take away the area of the triangle, which is, well, it's going to be a half R squared sine theta because it's half AB sine C. Okay, now we are going to use our equation here at the top and put in this and this into it and get one huge, great big expression. So we are going to say that a half R squared sine pi minus theta is equal to 3 lots of, it's terrible with this handwriting trying to fit everything in, half R squared theta minus a half R squared sine theta. Just about got it in. If you can just about read that, that's a square there. A bad workman always blames his tools, and that is exactly what I'm going to do here. This is totally about the fact that I'm using a touchscreen laptop, that the pen just doesn't seem to work very well, or is it the screen? I'm not sure what, but it's not me. It's nothing to do with me. It's entirely the fault of the computer. Okay, so you will see on all parts of this equation, or we can take out, let's make it easy by saying on the right hand side, you could take out a half R squared because you've got a half R squared here and a half R squared there. You take out that as a factor, and then you can see on both sides of the equation, you've got a half R squared. Well, if on both sides of the equation, you've got a half R squared, boom, you can cancel them out, and that just leaves us with sine pi minus theta equals, and we took the half R squared out and got rid of it. Let's take the 3 in. So you've got 3 theta minus 3 sine theta. Now, going back to my result at the start that I talked all about, so that's going to be sine theta, sine pi minus theta is the same as sine theta, and we've got 3 theta minus 3 sine theta. And to finish it all off, we've got sine theta on the left-hand side. So if we take it over to the other side, we've got 0 equals 3 theta minus 4 sine theta. Bob's your uncle. We've got the example done. It is quite a challenging example, couple of results, but hopefully you've managed to stick with me and read my handwriting. Here is the working once again. Drop me an email if you can't read any of this. But there you go. Pause as and when necessary. And then when you've done that, can you have a go at exercise 5D? Thank you very much. See you next time.